Welcome to this explainer. Today, we're diving straight into the absolute foundation of coding in Java. We're talking about how the compiler actually reads the raw numbers and fixed values that you type directly into your code. It's one of those things that, seems incredibly simple on the surface, but once you look under the hood, wow. There's this fascinating system of rules and little shortcuts that can make your code significantly cleaner and, honestly, infinitely more professional.
So let's get right into it. Picture this. You're staring at a screen of code and you see this exact line. Int num equals OB10101010. Now, if you're mostly used to standard counting, your brain might kind of short circuit for a second, right? Like, how does the Java compiler make sense of this confusing string of raw numbers and letters mixed together? And more importantly, how does it process this instantly without throwing a massive syntax error? Well, to understand the magic happening behind the scenes, we first need to get our terminology straight.
Section 1. Defining the Java literal.
Let's just skip the intimidating computer science jargon for a second. In plain, simple language, a literal is literally just you typing the actual value directly into your source code. When you type the number 10 or the number 1000, you are providing a literal. It's the raw data itself, hard-coded right there on the screen, rather than, say, a variable that calculates or changes its value over time.
But here's the thing. Sometimes Java needs a little hint from you to understand exactly what kind of literal you're giving it. For example, by simply adding a tiny suffix like an L to the end of 2000, you're telling Java, hey, treat this as a long-type integer, give it some more memory. Or, by adding an F to 20.5, you're explicitly commanding Java to represent it as a float. Think of it as a direct line of communication between you and the compiler.
Section 2. 4 ways to write integers. All right, so Java relies on specific prefixes to understand exactly which counting system your digits belong to. The first is decimal, our standard base 10 system, which requires absolutely no prefix. Just type the number. But look at binary, base 2. You need to prefix it with a 0 and a B, either lowercase or uppercase, so Java knows for sure it's binary. Then there's octal, base 8, which is famously tricky because it just requires a leading 0. And finally, hexadecimal, base 16, which is used all the time in memory addressing and colors. That one needs the 0x prefix.
So the absolutely crucial point here is this. Java is a highly structured language. If you want to use these alternative numerical bases, providing the correct prefix is absolutely mandatory, no way around it. If you try to write a binary sequence without that 0b, Java's just going to read it as a standard decimal number, and your math is going to be wildly, catastrophically incorrect. Or worse, if it has letters in it like hex does, it won't compile at all. That prefix is your strict contract with the compiler. Section 3. The underscore readability hack.
Okay, imagine staring at 1 million written out as just a squished string of 6 zeros. It is really tough to quickly read that without going completely cross-eyed or, tracing your cursor over it just to make sure it isn't 100,000 or 10 million. But visually proving why this next feature was invented, Java actually allows you to place underscores directly inside your numeric literals. The compiler completely ignores the underscores, it doesn't care, but for the human eye, it instantly reads as 1 million. It's a real game changer.
And this hack isn't just limited to standard millions or thousands either. Underscores can be strategically placed between numbers in almost any literal. You could break up a long, confusing binary sequence into neat 4-bit chunks. You can even use them to cleanly separate floating point digits right after the decimal. The only real rule is you can't put them at the very beginning, the very end, or right next to a decimal point. It's a pure readability feature designed entirely for the sanity of the programmer.
Section 4. Real numbers and scientific notation.
Now, whenever you introduce a decimal point, you enter the world of real numbers. Take the literal float 4.55f, for example. Remember that without the f, Java is going to automatically assume any decimal number is a double, which takes up way more memory. That f acts as the specific required suffix, designating it as a floating point real number. It's a small detail, sure, but memory efficiency is what separates the good Java developers from the truly great ones. But what happens when you need to calculate, say, the distance between planets, or the number of cells in a human body? You present massive numbers like 3.44e10. This right here is how you represent a gigantic scale compactly in Java, completely avoiding typing out some ridiculous string of zeros.
This is scientific notation baked right into the language. That e simply represents the exponent in scientific notation. It is directly telling the compiler, hey,
Take the literal value of 3.44 and multiply it by 10 to the 10th power. It gets stored as a double, and it ensures that your code remains elegant and readable no matter how astronomically large those fixed values become.
Which brings us to the ultimate takeaway from all of this. Look at the rules we've just covered, the underscores, the base prefixes, the scientific notation. While the Java compiler strictly handles how these literals are processed in memory, formatting rules like underscores exist entirely to make the code comprehensible for the actual humans reading it. So I'll leave you with this provocative thought. Are you writing code just so the machine can execute it, or are you writing code so the next human being can actually understand it? Keep your literals clear, use those underscores, and make your code a joy to read. Thanks for joining me on this explainer, and keep exploring.